Morning. Welcome to Krishna's classroom. We continue with our exploration of Lebesgue integral of measurable non-negative functions. This time we look at what are called the convergence theorems, because last time we introduced the integral and then explored its properties. That is what we have done so far. And what are the consequences? And one of the questions that we automatically stumble upon is the convergence problems. Okay, what is the problem? We have explored this earlier in the case of functions or measurable functions on sets of finite measure, and in that case we also put a restriction that they are bounded measurable functions. So we looked at this problem on bounded measurable functions on the typical question that we asked was this. The question that we had asked was, we are going to ask the same question. Okay? If where Fn belongs to this class, pointwise, say almost every point. Does it imply integral over E This is the question. That is, we can rewrite this in more clearly. Limit n tending to infinity integral over E Fn is this equal. This is the question that we have asked, and of course we got the answer that this is not always. Only conditionally it is valid. Only under further conditions like uniform boundaries, so let us ask the same question here for now. Let us ask the same question the new class we have considered, namely for Fn converging to F, pointwise almost everywhere, where each Fn and F is a non-negative measurable function. On E, not necessarily bounded. Not necessarily of finite measure. So this is what we are asking now. We have replaced these functions Fn by measurable non-negative functions and defined on E, where E need not be a set of finite measure. So this is the question. Obviously, we don't expect the question raised above. We don't expect limit n tending to infinity with no further condition. It is too much to ask for. It won't happen. Okay. Now, if you just look at the example we considered earlier, it will be clear that it doesn't. It also satisfies all these conditions that are here, but it doesn't happen. Okay. So this is the scenario. But then what else you expect? Okay, let us look at this. That means you need further conditions for this kind of limiting process to jump the integral. That's what it is. So here it means the following. Fn converges to F, therefore this limit n tending to infinity integral Fn equal to integral over E limit n tending to infinity Fn. So that means the integral comfortably jumps the integral with no change. That's what you your desire, if that is possible, but that doesn't happen. So let us look at some examples. Maybe we explore some examples. This would give some insight into what we can expect. So we'll take two examples. One, of course, E equal to 0. That's a set of finite measure. So measure of now we take Fn defined as n times the characteristic function of the interval 0 to 1 by n. That means on the interval 0, 1, see, the graph of the function looks like this. That is, you have 0 to 1 by n. This is 1 by n. Then you take the value of the function to be n. So what you define as this. So it's a kind of step function. So what happens is, as n increases, 1 by n goes to 0, but the value of the function starts increasing. Nevertheless, what you have is this. Fn converges to f which is identically 0 on 0, 1 pointwise. Therefore, f is identically equal to 0. So clearly in this case, you have strict inequality. What you have is this, that limit Fn, limit integral Fn is equal to 1, whereas integral f is 0. Because each integral is equal to so what we have is that is less than or equal to strictly less than this. This is the. Now we take another example. Examples 1, first example. Now example 2. There, of course, we have said that E is a finite measure. Now we take a situation where E is not a finite measure. Full of R. Take Gn, you define as characteristic function of then Gn converges to G is identically equal to 0 on R. This is pointwise. What about this? Here again, integral over G is equal to 0 is less than limit n tending to infinity So strict inequality is there in this case. Each of this, is equal to definition. Therefore, as such, one cannot conclude that if Fn converges to F, integral Fn converges to F. Crudely speaking, without telling such conditions. Then naturally, the sort of questions that you ask are, okay, if that is the case, what further conditions you have to use? I'll return to these examples when we start looking at further results. But let us see this. Okay. So we have a very fascinating result. It's useful in many contexts. What is called the fatosity. Which tells something more about this limit. Okay. This establishes the general position. So fatosity. Let us write down. Position. Use a bit more insight into what is going on. So we take the statement of let Fn be a sequence of non-negative measurable functions where each a measurable set. if converges F almost everywhere, then this is what you can say is integral over E. This is less than or equal to limit infimum over E. Now you have some idea of this. The limit infimum, you see, if you have a sequence which converges, then you have got two types of limits. One is the liminf, the other one is lim sup for the sequence. Now, if the sequence converges, then liminf is equal to lim sup equal to limit of the sequence. And otherwise, what happens is they become different. But liminf and lim sup exist, but not necessarily the limit. This is the scenario. For example, what exactly we mean by that? So let us look at some sequence. So this is the statement of the theorem. Before we come back to this, we make an idea of this. Let of numbers. Just define supremum of for n equal to. So you get a new sequence now. Take the supremum of the collection starting from an, call that Sn. So you have now a new sequence constructed. Sn is a new sequence that is constructed, and the property of Sn is that the namely that if you take S1 is greater than or equal to S2, So what you observe is that it's a decreasing sequence. Okay, right? So Sn is a decreasing sequence. Therefore, we can talk about the limit of this. So if you have a decreasing sequence, if it is a bounded decreasing sequence, then the limit exists. Otherwise, it becomes minus infinity. Okay. So limit this is what you call the limit supreme. Okay. Maybe m sub of now likewise you have limits. So we'll define In infimum of etc. So what happens? You have the following inequality. So it's a monotonically increasing sequence. Is monotonically increasing. So the limit exists. This is called, it may be infinity. This is called of limit of A. Now, what one can prove is that, and now we give an example to get some. Consider the sequence. One minus one, minus one. This. Now, what about the supremum of this? Now, supremum sequence is this. So, liminf is A, and in this case is 1. So, here the liminf okay. Now we can get an inequality also. It's not difficult. Get this inequality. Right. It will be a nice example to consider. So another example. You consider the sequence. Consider the sequence minus 1 to the power n. 1. Okay. Now you can see that the lim sup is a decreasing sequence. So you have what will be the lim sup? So you have got the so Sn equal to so the lim sup is 0, lim inf is also 0. So in this case the sequence is alternately positive and negative, but what happens is the lim sup and lim inf are both equal, therefore the sequence converges to. So you see that one can prove that the sequence converges if and only if the lim sup equal to limit. Okay. Otherwise the limits won't exist, because they are not going to be, the lim sup will be different from limit. Okay, so that's just a sort of digression, just to recall what it is so that you are comfortable with the terminology. Okay, let me come back now. So we come back to the Fato's lemma. So what we do is we try to work. See, our assumption is that Fn converges see, we assume the sequence Fn pointwise almost every. Which means there exists a set E naught E, measure of E naught equal to 0, where Fn may fail to converge. You can, if you want, but that's a set of measure 0. Okay, so that does not the conclusion of the theorem. Since once we prove on slash, so on E slash E naught, the sequence is assumed to converge pointwise or pointwise to F, and then you can conclude that F is a non-negative measurable function. Okay, so therefore we can, so we shall without loss of generality take E as self, or we shall simply assume that on entire E the condition is satisfied. That is, we assume pointwise on E. And no assumption on the measure of E or anything. All that he says, it's a measurable subset. And we have assumed that Fn is a class of measurable functions which are non-negative. So what we have is this: basically we have Fn non-negative, now we have measurable and converges pointwise then f is non-negative and measurable. So this is something which we have proved earlier. Okay. Now, what is our strategy? What is that we want to? We want to show that integral over E f limit infimum of this is what we want to. So how is this integral defined? Because we have approximated this using what is called the see, this is what you have. So we approximate f by approximating f by bounded measurable non-negative functions with finite support. Such that this is what we are doing. So we take approximate functions f from below by functions with a lot of nice stronger properties, like it's a this h is taken as a bounded measurable non-negative function which lies between 0 and f. Secondly, to see that h has finite support. That means outside a set of finite measure, the function takes the value 0. So that's the sort of approximation. Again, for such functions, we already have developed the theory. Therefore, the integral is well defined and so on. And for each such function, you get an integral. So you get a class of functions or a class of numbers, real numbers, when you take the integral of such functions. And this set may be bounded above, but they are all non-negative numbers, may be bounded above or may not be bounded above. That we don't know. Okay, if it is bounded above, then you take the supremum, and that supremum is defined as the integral of f. Otherwise, the integral is defined as infinity. Okay, so that's the definition of this. So we work with such functions. So a moment's thought tell you that the strategy would be to prove the following. So it is sufficient to prove that integral over E H is less than or equal to limit infinitum over E for every H bounded, measurable, bounded, measurable function with finite support and such that because what you call this is this integral over f. This is equal to supremum of h. Such h. This is the definition that we take. Okay, all these are well defined, and we have analyzed all these things, and in terms of that we have defined this. Therefore, it is sufficient to prove that for all such h, this inequality. That's the strategy. Okay, what next? What do we do next? So let us proceed with this in this way. Now note that let h be such a function. Let m be the bound h, that is mod h less than or equal to f. That's the assumption. So m we take it that. So now let E naught be the set on which this is the support of E. Then what you have is measure of E naught is, because you are working on H, okay. So now we are in a position to define, now we in fact everywhere on E, okay. So let us prove this, rather E, okay. So let us define H. Define as now H is measurable, Fn is measurable, and Fn are measurable, which implies Hn are measurable. And here we also have, you see that mod H is less than or equal to Y. That would follow. Oh, okay, this is what we want to follow, to prove. So let us now show that Hn converges to H. So our claim is that Hn converges to H. Now we also have 0 less than or equal to Hn less than or equal to F on E dot and Hn equal to so these are all bounded. So Hn form a collection of bounded measurable functions with on a set of finite measure that we shall prove. Therefore, once we observe this, then you see that it is easy to Easy to read out the whole thing. Okay. Now we see that for every x belonging to E, Hx is less than or equal to Fx. And our claim is that how do we prove that? So let us prove this. The proof of this is as follows. At x where Hx is less than or equal to Fx, we have Hnx equal to. Okay, how does this come? Look at the definition of Hn. Okay, so suppose, look at this. Suppose this is your E. Now suppose this is your F. Now what about H? H is some function like this. Okay. Now I am taking E to be of finite measure in the picture, but that not necessarily the case. So this is what you have. So, or let me revise the picture. The picture is, let me take E to be something like this. So let this be. Now what do I have? I have F defined something like this. Now what do I have? I take H, something with the support of, this is the support of okay. On this is H defined where H is equal to 0 here, H is equal to 0. Now suppose I take Fn. So let Fn be something like this. This is V some Fn. Okay. Then what is your definition of Hn? Hn is defined as follows. Fn is defined, then see what is, how is Hn defined? Hn is defined as minimum of H and Fn. Now here H is 0. Therefore, what you have is the following. So, this is your Hn over here because it is 0 all over. Okay, because H is 0 here. Now, over this place, how do you define? Define it as follows. Now, on this one, see, this is your H, this is your H, and this is your Fn. So, you have to take the minimum of this. So, it is defined as this one of this, and from here on, it is again the minimum of it is equal to Fn. On this portion, it is this. So, the function Hn is this over this, and over this portion it is this, and then this, and over this. This is your Hn. Okay. So, a few things are clear. Hns are all bounded by M. Clearly. Okay. Secondly, that is because they are bounded by Fn. Okay. Fn are bounded by M. So, Hn are all bounded by M. So, that condition is satisfied. Secondly, what you have, Hn is measurable. Hn has support which has finite measure. Okay. So, Hn satisfies all the requirements of the earlier class that we have looked at. So, it is bounded above by Fn. Okay. So, first thing that you observe is at x where Hx is less than Fnx. Okay. Yeah, this is your H. Hx is less than Fnx. That is the portion where what is Fn? Fn is this one. So Hx is less than Fnx is where this happens. Okay. You have this equal to H itself. Right? So that is clear. So Hn is equal to H. So this part we have added. Then what more? Yeah. Therefore, Hn converges to. So what is the conclusion? Where that is there. Secondly, now we take at x where Hx is greater than Fnx. That is where this happens. Hx is greater than Fnx. Okay. This is your h. This is h. So if fx is hx is greater than fnx is this. So these are the portions. This portion. There you have hnx equal to fnx. Then hnx converges to fx, which implies hnx converges to f of x, because hnx is equal to fnx. Okay. So that is there. Now this is the scenario that you have. You have fnx which is equal to hnx, and this is less than hx. This is less than or equal to f of x. Therefore, fnx converging to implies as hence what we have is that hn converges to h as now integral h, this is what we wanted to see. What we wanted to prove was integral now we will look at this collection hn. HNs are bounded measurable. With finite sum. With finite sum. HNs are uniformly H is also with finite sum. Therefore, this is what you have. So, what is the conclusion that you have? By application of bounded convergence theorem, well, you can apply bounded convergence theorem here because you see that all the set conditions are satisfied. We have limit n tending to infinity this is equal to because this is the finite support of E naught is the finite support of Hn. Now this is equal to what? Because you see limiting process applies, limit can jump this, therefore this is integral over E naught H, and this is equal to integral over E. So we shall use this. See, what we wanted to prove, this. We wanted to show that integral over E means so let us try to work it out. So what you have, so you see that integral over E H, this is equal to limit n tending to infinity integral over E, that we have already proved that. And what is that? So if the limit exists, then it is going to be lim inf is going to be equal to lim int. So what you have is, this is actually lim inf of because the limit exists, so the limit inf is equal to limit. And this of course is less than or equal to Fn. Okay, this is what you get, right? Okay, because you see that Hn is less than or equal to, so lim inf of integral Hn is essentially less than or equal to lim inf of Fn plus. So this is the reason for this. Okay. And now you see that take the supremum. Over all H on the LHS of star. Then we have integral over E F less than or equal to next. So that completes the proof. here. And we have seen that you cannot expect equality to hold in this case, in general. Okay, we have seen examples where it doesn't happen. Remark, so let's put that as a remark. Strict inequality may hold as we have seen in this theorem, as we have in both examples. We have looked in. So that is one of the conclusions. Okay. Therefore, you see that if you want equality, possibly you need further conditions. What are those conditions? That is our exploration. So further remark, 1. For equality to prevail, we need hold we have to have more conditions on the sequence. We shall explore this in our next lecture. And I think we will conclude it here. And this is one of the important results that you have in this regard. It throws a lot of insight into the intricacies that are there regarding the limiting process. Okay, thank you very much.